Hello class, this is the other part of the Fugacity calculation. So here I want to show you the Fugacity calculation using Henry's law. So this is again Fugacity calculation using Henry's law. So the first example, which I also had that in lecture 16, this problem is coming from problem 2. This is example 3 of lecture 16, which was a problem 2 from final exam of 2016. So let's try to take a look at the problem statement. So it says at 25 degrees C and 1 bar partial pressure, the solubility of ethane in water is very small. So whenever you see very small dilute, then this is a strong hint of using Henry's law. It says the equilibrium mole fraction is indeed a very small value, 0.33 10 to minus 4. And then we are asked to calculate what is the solubility of ethane at 25 degrees C when the partial pressure is now 35 bar. So according to the problem statement, the temperature stays the same, but the pressure is changing from 1 bar to a higher 35 bar, and we notice that this pressure is always referred as a partial pressure. And the other condition is assume that at 25 degrees C the compressibility factor of ethane is given by the empirical relation Z, compressibility factor Z, as a function of the pressure, where pressure is in bar. Also at 25 degrees C, the saturation pressure of ethane is 42.07 bar, and that of water is 0.0316 bar. What is that implying? So this is the saturation pressure of ethane is 40 some bar, and the water is 0.03 bar. Looks like the saturation pressure of water is extremely low. So we could somehow treat the vapor phase as if it's purely coming from ethane. Assume Henry's constant does not change in this range. So the pressure is changing from 1 bar to 35 bar, but we assume Henry's constant does not change in this range. So we need to calculate the solubility. So this is a problem of ethane in water. Let's try to use Henry's law. And temperature is always 25 degrees C. Pressure P1 is 1 bar. Moving to P2 is 35 bar. And for the first condition, we understand that fugacity of, so let's call this as water is as the component 1, and this is my component 2. So I would have F2 at 25 degrees C 1 bar. F2 is X2 times H2. So I know this X2 value, and I don't know this H2, right? This is the component 2 in the liquid phase. But of course we want to ask at this condition what is my corresponding vapor, right? because I could take advantage of the third equation, which is F2 in the vapor phase is F2 in the liquid phase. And then the temperature stays the same. The pressure is increasing from 1 bar to another higher 35 bar. Now we want to figure out at this new condition F2 of this liquid. Let's call this F2 prime. Then we are still using this Henry's law to calculate, and Henry's law for that equation the constant does not change. So we assume this is x2 prime times still the same x2, right? And of course we don't know what would it be f2 prime for the vapor phase, but no matter how, I still have this equation valid. So this is after reading the problem statement and understand we are going to use Henry's law, what we could easily have. So now let's take a look at the other known condition, especially the one that at 25 degrees C, this is not depending on the pressure, of course, because it's the saturation. So at that temperature, this saturation pressure of water, which is 1, is 0.0316 bar, while the saturation pressure of 2 is much larger. So that actually implies for this vapor phase, which is normally composed of water and ethane, this would be, we can treat is composed of ethane itself. Okay, so this is the hint from the known condition. And the use of this is now we can understand this y2 is almost 1. Okay, so if we have this understanding and the partial pressure at the first condition is 1 bar, then we can have the following calculation at 25 degrees C and 1 bar, which is P2. Mainly coming from this P2, then we can have this fugacity of component 2 in the vapor phase is Y2 times P total, which is Y2 times P2 is 1 times 1 bar is 1 bar. This is my calculation of this component 2 at the initial condition. So now you can see that using the general equation, which is F2 in the vapor should be exactly as F2 in the liquid, which is X2 times H2. Okay, so here I know the fugacity of the vapor phase, which is 1, the solubility of component 2 at condition 1 is 0.33 times 10 to the negative 4 times H2. So from this equation I can calculate the Henry's constant, which is 1 over 0.3324. Now I'm having 3.03, right? So now we are going to have the pressure change. So now pressure is 35 bar. H2 stays the same. Okay. How about the vapor? So at 1 bar, we treat the vapor phase as an ideal gas of, but at this 35 bar, the vapor phase can be still treated as the pure component 2, but we cannot treat it as an ideal gas. So we need to calculate the fugacity of 2 prime in the vapor phase. Okay, that is the core. However, we would still have the general equation. However, we still use F2 prime in the liquid, which is X2 prime times H2. This would be F2 prime in the vapor phase. But now this is not, which is not this Y2 prime times P total. Okay, simply because ideal gas not an ideal gas at 35 bar. So now instead of using this Y2 times P total, we still can use the fugacity coefficient definition. So if you recall, I have F2, which is the fugacity coefficient of component 2, that is always defined as F2 over P2, right? So there we could have F2 in the vapor phase. Here the vapor phase, we use the fugacity coefficient. Otherwise, we probably use activity or activity coefficient for the liquid phase. So F2 in the vapor would be phi2 times P2. How about P2? P2 is still, we use the same assumption. This is almost 1, then we have this P2 is 35 bar. The problem is this phi2. Okay, we need to figure out what is that fugacity coefficient. But if we want to complete this equation, then this would be my phi2 times P2. Okay, this is known. That is calculated just now in order to figure out x2 prime, the new solubility, then we need to calculate the fugacity coefficient at this higher pressure. Now when you check the problem statement, we are still having this z as a function of pressure. We have not used this equation. And that year of the exam, we provide the supporting equation for the general fugacity calculation. And the equation we are going to use is based on this equation. Log phi I would be the integration from 0 to p using tpx. This is Vi partial molar pressure of component I over RT minus 1 over P dP. Okay. So we feel like we have to use this in order to calculate the fugacity coefficient of 2. But how we are going to use this z, and we know z is a function of pressure minus 7.22 times 10 to the p squared. So we don't know what to do about this term. So if that is the case, let's try to take a look at the definition of z. So z for a mixture z is defined as PV over MRT. Okay, this is V, this is N. That is P V I partial over RT. Okay, that is for the vapor where Y2 prime is almost 1. So this this Z2 is going to be P V2 partial over RT. So if this is the case, then we can using this equation 1 from use equation 1, then we would have Vi over RT, which is V2 RT is Z2 over P. So log phi 2 is from 0 to P V2 partial over RT minus 1 over P dP, which is 0 to P. This is Z2 over P minus 1 over P dP, which is 0 over P Z2 minus 1 dP. What is this Z2? Z2 is known. P Z2 is 1 minus 7.63 times 10 to P minus P squared. This is Z2 minus 1 dP. Okay. So this would be 0 of P and then of course we are going to run this integration. This is log phi 2. Okay. So now we use P is 35 bar. Then we can calculate this log phi 2. It's basically 0 from 35 2 more steps of simple math. You can calculate phi 2 is 0.733. Okay, so now we understand the fugacity coefficient. Then we go back to the equation x2 prime times the sin h2 is my fugacity coefficient times p2. What is p2? P2 is basically my p total. Where y2 prime is still very close to 1, then we say p2 is p total. Okay, so we have this calculated. This is also known. This is 35 bar. Then you put all those numbers. You can easily have x2 prime times what would be 5 times 35. So there I could have x2 prime. The new solubility is about 8.47 10 to minus 4. Still reasonably low, so this is why we are using the Henry's law for the fugacity or the solubility calculation. Okay, this is the first example. And the other example is this example 4 of lecture 16. This is example 4, which is the problem 3 of final exam for 2015. Okay, try to insert this. Okay, let's read the problem statement all together. So the problem statement says estimate the solubility of hydrogen component 2 in liquid propane component 1 at 255 Kelvin and 100 atm partial pressure of hydrogen. This is the partial pressure of hydrogen. And the pressure is pretty high, so we probably need to give up the ideal gas behavior. The problem statement says assume that Henry's law applies. Critical temperature of propane T sub C would be 369.9 Kelvin. why we need to use that critical temperature, right? We don't have a clear view of this. The following data is also available, which is H2 in 1 for the P1 saturation, which is the liquid propane saturation pressure is 1300 atm. This is a little bit strange, so we need to understand this. This is V sub 2 at infinity partial volume is 51. What is that? P1 set, which is the saturation pressure of liquid propane, is 2.5 atm. The Fugacity coefficient of component 2, which is hydrogen, in the vapor phase is 1.01. Okay. And now it says H21 P1 set is the Henry constant for hydrogen in propane at 255 Kelvin and at the saturation pressure P1 set of propane. V2 infinity partial is the partial molar volume of hydrogen at infinity dilution in propane. Since the temperature 255 K is well below, okay, this is the explanation. The temperature is well below the critical temperature of propane. We assume V2 infinity partial is independent of pressure in this problem. Okay, so if the pressure is changing, then we don't need to worry about the partial molar volume of hydrogen. And then the fugacity, this is the fugacity coefficient of hydrogen in the gas phase. So this is a pretty tough question, simply because after reading the problem statement, we don't have a clear view of where to start and what equations to use. So if that is the case, let's try to understand what we normally start. What would be the useful general equations for us? So number one thing is let's try to write down the equations. First one is definition of chemical potential. We always want to write down this is mu I as a partial derivative of G dmi at T temperature are the components fixed. The second is definition of fugacity, which is d mu I is RT d log Fi. Okay. The third is since we are having this partial molar volume of hydrogen at infinity, so there we try to recall we had one very useful equation, which is d mu I over dp while keeping temperature component fixed. This is Vi. This is my Vi partial. Right. So if this is the case, then from, let's call this equation 1, equation 2. Okay, I'm losing this connection. Alright, so with that equation 1, 2, and 3, we could have the following. I'm going to replace this partial mu I by RT this is partial RT this is RT partial log Fi dp, which is of course still Tn is fixed, which is partial log Fi dp Tn is Vi partial over RT. This is equation 4. So I feel like we have to use this partial molar volume, but not quite clear. Then the problem statement also says that we are going to use the Henry's law. So what is Henry's law? Henry's law says component 2 hydrogen solubility in the propane would be X2 times H2. Okay. So here's a little bit challenging part. So now if you try to combine this equation 4 and equation 5, so you see that we have a term called partial log Fi, and I have the Fugacity definition over there. So this is why we want to further simplify from this equation 4 for the left hand side, this partial log Fi, which is F2 P Tn is indeed partial log X2 times H2 dp, keeping temperature composition fixed. Then we try to separate the two terms. This is partial log X2 over dp Tn plus partial log H2 over dp Tn. Okay. What else we have? Well, for this equation 5, that implies that X2 goes 0. This is how Henry's law is valid at this dilute condition. So if this is the case, then we could add this X2 goes 0 to this equation 6. Tn. So now if X2 goes 0, then the first term will be 0. Right? The second term is still at a fixed temperature and composition. And according to my equation 4, this has to be Vi partial over RT. Vi is basically V2 now. Okay. So what is that equation? Well, this is we have some. This is log H2 over dp. Of course, temperature is a fixed value. This would be V2 partial over RT when X2 goes 0. Okay. So when X2 goes 0, the partial molar volume we actually have not discussed that, but we will have that discussion this coming Monday. This is the infinity. Okay. So this is how we feel like this is the right direction, because the problem statement has some information about this V2 infinity partial. So now if we are going to use the provided information, one is the saturation pressure, right? It's, the saturation pressure we have is P1 set, and then we are going to calculate the solubility at 100 atm. So we know this is the first saturation pressure, and then this is the saturation pressure, or the P2 is 100 atm. So this is why we decided to run this integration from P initial, P1 set, to P final. What is that P2 final? We from the problem statement we know this P2, the partial pressure of hydrogen is 118. How about P1? And the problem statement says the for the liquid problem we know this this is P2, which is 118 plus P1 set, right? This is a vapor, majority in the vapor of 2. So this is 100 plus, this is 2.5 atm. This is 100 plus 2.5, which is 1 over 2.5 atm. Okay, so if that is the case, then we are going to calculate, this is d log h2 from some value to v2 infinity of rt dp. So this is the initial is p1 set. This is for the final p. This is again p1 set. This is for the p final. So there you can see this is log h2 of the p final H2 of P1 set. You see, we have that information. So this is a perfect choice for this calculation, which is V2 infinity of RT. The problem statement says this is independent of pressure. Independent of pressure. So this is a constant. So this is why if we take a look at this integration, this is basically P final minus P1 set. Okay. This is a fixed value. This temperature is known at 255 Kelvin. This is also a known quantity. This is also provided. P final is known, P set is known. So we are going to have this equation. So this is log right H2 P final. That value we don't know, and Henry's constant is depending on the pressure. This is V2 infinity partial 51. Keep that in mind that we need to convert this to 10 to minus 6. So now I'm going to have all the SI units. Right. P final minus this is P set. Okay. So this is one equation we are setting up. So basically we figure out the Henry's constant and its dependence on the pressure. On the other end, we also have this Fugacity coefficient. I have not used that. This is the Fugacity coefficient of hydrogen in the gas phase. So for the gas phase, for the vapor, so this is for the liquid phase. Hydrogen. Henry's constant. Okay. So now for the vapor phase. Also for hydrogen. The problem statement says this is phi 2 for the vapor phase. From the definition, that should be the fugacity of hydrogen in the vapor over this P2. P2 is the partial pressure. This is 100 atm. And that value from the problem statement is 1.01. So from there, we figure out the fugacity of hydrogen in the vapor phase should be 100 times 1.01 is 101 atm. Okay. Then, of course, we need to set up the using F2 in the liquid should be always F2 in the vapor. That's the universal equation. Then F2 of the liquid would be what? This is the X2 times H2. Now H2 is depending on the pressure, so let's call this P final. okay, which is F2 G is 1 over. Okay, so if this is the case, then we can calculate this as while H2 P final is from, let's call this as equation 7. H2 P final is exp of this. Right, this according to my calculation is exp, this is a value. So therefore I'm going to have this x2 times xp should be my 100. So from there I figure out eventually solubility of hydrogen in this liquid propane at this 2.5 total final pressure is 0.0609. It is indeed a quite small value, so it justifies the use of Henry's law. So eventually we have this problem solved. And if we take a look at the problem statement, this is a pretty strong hint that we would use Henry's law, but we need to figure out the dependence of Henry's constant. Otherwise, if Henry's constant does not change as a function of pressure, then we would have this as H21, probably just this as 1300 ATM instead of describing this P1 set. And that is also a strong hint over here. Now we have set up this equation and we want to somehow create this P1 set. Okay, so this is why we pick up this as my initial. So this is the most challenging part of this problem. Otherwise, there we tend to use standard or ideal gas condition or some known property. Okay, so this is indeed the third case that we know some special value at this specific condition. So this is why we try to make this as my initial. Okay, and over here we try to make the problem relatively easy. Otherwise, this V2 should be a function of the pressure in general. But now the problem statement says this is a fixed value. So those parts are actually making the problem solvable, but still this is a very challenging problem. I used this in 2015, but I have not had any problem that challenge coming from Hermits constant. Okay, so I want to share these two problems with you, but of course you can read the old exams with their solutions from Canvas, and let me know if you need any further discussion. Thank you.